In this lesson, we're going to look at the absolute age. So in the last lesson, we talked about relative age. We said, how do we look at the age of something compared to something else? In this lesson, we're going to talk about dates. So here's our geologic timescale. And the relative age tells us that the Pliocene happened before the Pleistocene, which happened before the Holocene, which is what our recent time is. That's how we got that's the relative part of it. The tertiary happened before the quaternary. But to get those dates, we need to use some different techniques called the absolute dating techniques. And so we've got a number of different ways that we do that. And once again, we're going to go through these on your handout. Once again, if you haven't printed out your handout, please go to Canvas and print out your handout. You're going to have the same thing that you did with the last one. You're going to have a place for the description of what each one of these is, and then a place to draw a sketch to go with it. So, radioactive decay. I want you to think of uranium. So uranium is what we used in atomic power, and when we split the atom, right, we release energy. But if we don't split the atom and we just have that uranium by itself, it's still going to emit heat. It's going to change over time because of radioactive decay. It's going to be breaking down into what are called its daughter isotopes. So an isotope is a version, basically, if you will, of an element. So we have an atom that has a certain number of electrons, right? And then we have the isotope, which is almost the same, but it has a different number of electrons than the parent did. So they look at the amount of that radioactive material that's still left within the rock. Now we think of radioactive, right? And we think of the big yellow sign and we think of danger, you know, because we think of uranium. But almost all rocks go through radioactive decay, and it's not always a dangerous thing to be around. So you're going to be doing an activity in one of the later lessons that has to do with radioactive decay and how do we look at how many of the parent isotopes there are versus how many of the daughter isotopes there are. Radiocarbon dating is similar. In radiocarbon dating, we could do this with things that were alive. Radioactive decay is for rocks and non-living material. Radiocarbon dating is for living materials. So we use this in geology, but this is the same kind of thing that you would hear about if you've ever watched any like Discovery Channel or, you know, those kind of documentaries that talk about the ages of things. So one that comes to my mind is the Shroud of Turin, when they take samples of it, or they do this in archaeology all the time. They'll find a pit house that has some of the wood left in it that was part of the ceiling. They can take a little sample of that and they can find out how much carbon there is that's left in that material, and because carbon, just like our radioactive isotopes, it breaks down at a constant rate over time. And so when they see how much of it is left within that sample, then they can give you a date of how old it was. And you know, there's a plus or minus. It's a range, but they're getting much better at the radiocarbon dating in particular, and they can get pretty close. Dendrochronology is where we also use the tree rings. So we don't just use the radiocarbon dating part of it, but we can also tell how many years the tree lived. So for example, they might use this in combination with radiocarbon dating. So they have the tree, they know how long the tree lived for, and then they can use the radiocarbon dating to see how old the tree is, so they could say, and that's where they start to get dates going backwards. So if it's a freshly cut down tree, well, we can count the tree rings and go back to the middle and figure out how when the tree, you know, germinated and became a tree. But if the tree's been dead for a long time, or it's been in, for example, a Native American dwelling or something like that, they'd use the radiocarbon dating to pinpoint the date that the tree died. And then they use the tree rings to count back to see when it was alive. Tree rings hold some information for us that is useful to all sorts of different kinds of scientists. The tree rings themselves, there's two different rings that are laid down each year. There's early wood and late wood, and so we only count every other ring essentially. But what it tells us is that the early wood is laid down in the spring, and then the late wood is laid down usually after the tree starts to go dormant. And the distance between the rings can tell us how much water there was during that year. So we can tell when there was times of heavy rainfall. We can tell when there was times of drought. We can tell when there were fires because there are scars that will get preserved. So if the fire actually burned the bark of the tree and burned to where the ring was, it'll actually leave a black mark. in there. And so we can tell when there were major fires in a time. We can tell if the tree lived in an area where the trees were really densely packed together, because if there's lots of competition for light in particular, then the tree rings are also going to be really close together. So they can tell climate information, they can tell about what it was like when different people lived in areas, so they can get lots of information from tree rings. Ice cores, now ice cores they have to do in ice packs. So we're looking at the Arctic, the Antarctic. They can do ice cores in the glaciers that stay around all year long. And so we're looking like in some of the higher mountain ranges, in the Alps and things like that. So what they do is, if you've seen that movie Day After Tomorrow, I know it's getting kind of older now, but at the beginning he's got this big drill and he's drilling down into it, and he says we're looking at these ice core samples. So the layers kind of look like our tree rings if you look at them on the side here. So this is a sample of an ice core. This is a picture that they took of it. And so we get the amount of snow that was laid down during a particular year. Okay, so each one of these lines represents a different year. Some of the cool things they can find out about the environmental conditions is they can look at like how much snow there was. They can see if there was a big melt back in times. And they can also tell what the atmosphere was like. They can, when you put water into a freezer and you get your ice cubes out, sometimes there's an air bubble that's in your ice cube. Well, the same thing happens in these ice core samples. There can be bubbles that are in there, and they can actually extract air out of that bubble and then test it. And they can see what was the carbon dioxide level, what was the methane level. So they can sample different gases in the atmosphere and to see what it was like during those times. They can also tell when there were catastrophic fires or volcanic eruptions, particularly when smoke columns went all the way around the planet. So a few years ago, in Iceland, when the volcanoes were erupting, remember, and it like disrupted plane patterns, they had to fly different directions, and that ash went all the way around the planet. The same thing when Mount St. Helens erupted in 1980, the same thing happened, and some of that ash then falls on the ice packs, and it gets layered over with snow, and it gets packed down in there, and so they can tell when the history of when these larger events actually occurred. A varve is kind of like an ice core. They do it the same way. They drill down into it, but now they're looking at clay that's in the bottom of lakes. Once again, the sediment settles down right from the surface. And so when things like ash and pollen and plant material and stuff like that settles down over time, it gets trapped in those mud layers. They can also tell about what the salinity of the water was, how much salt water there was in there. So they can tell if an area actually was once a freshwater lake and then became saltwater, if it's saltwater and became freshwater, because they're going to see different critters within the layers, but they're also going to be able to tell how much salt was actually in the mud itself. So they can tell lots of different information from the bottoms of these lakes that have been there for a long time. So this is called a varve.